So this group of instrumental techniques focus on the interaction between electromagnetic radiation and matter. So basically, the way we classify optical techniques is based on the region of the electromagnetic spectra that you are utilizing for analysis. Okay? And this region of the EMR is characterized by its energy, or more obviously, we usually use your frequency or the wavelength range. Alright, so nandyan yung UV-vis, no? UV visible region. You have your infrared region. Alright, microwave, radio wave, X-rays, you know. So those are the uh, various regions, no, of the electromagnetic spectra. And hence, we have techniques like UV-vis spectroscopy or infrared spectroscopy, no? So again, we classified the optical methods based on the region of the EMR that we are utilizing. So when EMR interacts with matter, there are different interactions. Alright, and we also utilize these interactions, as you will later see in the succeeding slides. Okay, so first let us discuss the theoretical aspects, a review of the theoretical aspects of EMR. Okay, so shown here is the is an illustration of your electromagnetic radiation spectra. Okay, so a good reference point would be this narrow region here, which we call the visible region. Again, we call it visible region because it's the region of or it's the range of wavelengths that is visible to the human eye. Okay, so roughly it's around 400 nanometers to 700 nanometers, no? So from the color violet to red. All right. Now, so some review about the units, no, or the variables used to describe light, no. So again, we have your wavelength. All right. Usually the unit is in nanometers, but in the case of this equation, wavelength here is in meters. And then you have the Greek letter nu, which refers to the frequency. Alright, so frequency is again the number of cycles per second. Alright, and since we are talking about electromagnetic radiation, the speed of light, or EMR, is a constant, no? We accept it as a constant, no? 3 times 10 to the 8 meters per second. Alright, so another equation used is how to compute for the energy of a particular frequency or wavelength of electromagnetic radiation. So we have this equation where H is your Planck's constant. So you have to memorize this value. So again, if you're using this equation, nu should be in hertz or per second, and lambda should be in meters. Okay, and then the resulting unit for energy would be joules. So as we can see from the equation here, frequency is directly proportional to your energy, whereas your wavelength is inversely proportional to your energy. So meaning to say, the higher the frequency of electromagnetic radiation, the higher the corresponding energy. Likewise, the higher the wavelength of electromagnetic radiation, since there's an inverse relationship, the lower the energy becomes. Alright, so we go back here to this illustration. So again, beyond red, you have your infrared region. Alright, so wavelength wise, it is of longer wavelength, of course, and because it is of longer wavelength, it has lower energy. Alright, and Some examples of infrared radiation would be that of your oven toaster and your heat lamp. So those used to heat food. All right. So infrared, visible light is more energetic than infrared light. No. So infrared, um, but this will not be able to induce your so-called electronic transitions. So we'll go to the topic later. Okay, but it's capable of inducing vibrational transitions. No, so meaning to say it makes your chemical bonds vibrate. All right. Now, going further from the infrared radiation, infrared region, you have your microwave region. All right. So again, it's of longer wavelengths. All right. So examples of usage of microwave, so cellular phone technology, microwave ovens, etc. In chemistry, although we will not discuss this one in this module, one example of an instrumental technique using this is your electron spin resonance spectroscopy. All right. So going further away, no. So again, much longer wavelength, much lower energy. You have your radio waves, no, or the radio frequency, typically used in broadcasting, so radio, television. So in instrumental techniques, NMR, nuclear magnetic resonance spectroscopy, uses this particular region. So again, we'll discuss this more later on. Now, going back to the visible range, so going farther away from the violet region towards the left, you have your ultraviolet region. So again, as you go shorter wavelength, higher frequency, you have higher energy. So when it comes to interaction with matter, it has a more penetrating interaction. All right. So ultraviolet is also used in spectroscopy, in tandem with visible. So you call that your UV vis spectroscopy. So again, this allows you to induce what you call electronic transitions in the valence band of the atom or the molecule, the valence region. So going beyond UV, you have your X-rays. Again, more penetrating. Although we will not discuss this one here in this module for CI, X-ray techniques allows you to have electronic transitions in the inner core shell of the atom. Alright, so X-rays or X-ray based techniques are usually used for elemental analysis. But later we will show you another application, of radiochemical techniques, in analytical chemistry. So beyond X-ray, you now have gamma rays, which are of course very very energetic. All right. So again, for this slide, you have to remember how to interconvert wavelength to frequency using this relationship, and how to compute the corresponding energy of the particular EMR radiation. So this figure shows you the different interactions of EMR with matter. Alright, so when you refer to EMR's light, technically you are referring to the visible region only. Okay, so yeah, okay. So basically, these are the interactions, of EMR with matter. So you have transmission. Transmission pertains to the passage of light across a medium, or in this case, your sample. Now let's call this your sample, right? Now, transmission is related to absorption. So please correct this one in your modules, no? So when light passes through a medium, okay, most of the time, some of the energy of the incident radiation is absorbed by your sample. Alright? So the greater the transmission, the lower the absorption. So when you say you have greater transmission, there is lower, or there is lower attenuation, no, in the energy of transmitted light, meaning to say that the energy of the transmitted light is retained, no, or the energy of the incident light compared to the transmitted light, no, walang change, no. So that is when you have very low absorption. But if you have very high absorption, the energy of the transmitted light is much lower. Not energy, the power, no, the power or intensity of the transmitted light becomes much smaller compared to that of the incident radiation. All right, so these two interactions are the basis of absorption spectroscopy. So well, you're familiar doon sa mga yun, no? So you have your AES, no, atomic absorption spectroscopy. You have your UVV spectroscopy, which is again based on the absorption of UV visible radiation. You also have your infrared spectroscopy. Okay, the transmission setup, transmittance setup for FTIR is based on absorption of infrared radiation. Even NMR, no, nuclear magnetic resonance spectroscopy, is also based on absorption. Okay? Yeah. So we will discuss these two in more detail in the succeeding slides. Okay? Next, you have reflection. So reflection pertains to the bouncing, no, of radiation over a surface. Now, from physics, optics, reflection is defined as the bouncing of radiation on a surface, all right, wherein the angle of the incident radiation, we call that the angle of incidence, is equal to the angle of the reflected radiation. So those angles are measured based on what you call the surface normal, okay, which is an imaginary line perpendicular to the surface. All right. Next, you have your refraction. We know refraction as the bending of light as it passes through a medium, and this is caused by the difference in refractive index between the two mediums, no? So remember, air or vacuum is your medium 1, for example, and medium 2 would be your sample. All right, so there is a bending of light due to the difference in what do you call this, your refractive index. Now, if you remember from your I think you discussed, or you had an experiment on this, no, in physical chemistry. We know that refractive index can be used for sample analysis, no. You call that technique refractometry. All right, and if you did some OJT, no, in a food manufacturing company, if you've heard of the so-called bricks, degree bricks measurement, which is used for measuring sugar concentration. All right, it's based actually on refractive index measurement. Okay, diffraction is when you allow radiation to pass through a very small opening or a narrow orifice. Okay, and one example of optical technique using diffraction is your X-ray diffraction or X-ray diffractometry. So the gaps between atoms in a solid sample or a crystalline sample serves as your small gaps, no, or small orifice. All right, wherein when X-ray radiation passes through, diffraction happens. Okay, so basically, what happens that your radiation gets scattered. Diffraction, one common example of diffraction would be the one you see in CDs or DVDs. Di ba? Pagka binaligtad mo yung CD or DVD, you see this parang rainbow reflection. Alright? This rainbow reflection is caused by the diffraction of white light. No? Because there, in the surface of the CD, there are microscopic what we call this, grating like patterns, no? In the on the surface of the CD. So this causes the diffraction of light, which basically breaks it apart. All right, and this is the phenomenon utilized by your gratings. No, by now you know what gratings are. So this is a type of dispersing element, no, in monochrometers. All right, used in spectroscopy. Okay, then you have scattering. So scattering pertains to the scattering of light. So when light interacts with a certain sample, that particular radiation scatters. Alright, so paano ba? You can imagine light as parang cue ball siguro sa billiards, no? So when you shoot the cue ball sa billiards, all right, when it hits the other billiard balls, it gets scattered. All right, now the scattering of light, maraming effect yun, no? So if there is no change in the energy of the incident light versus the scattered light, you call that elastic scattering. Okay, wherein the energy or the momentum, sabi nga, no, in physics, of the photon is conserved. However, there is also what you call inelastic scattering. Okay, wherein there is a change in the energy between the incident and the scattered radiation. And basically, this inelastic scattering is what makes Raman spectroscopy possible. Alright, so although we will not discuss here Raman spectroscopy anymore, Raman spectroscopy is a technique that is based on scattering. Alright, reflection, meron din ng mga techniques, no, for, based on reflection, but more of sampling techniques. Okay, but basically the data obtained is still converted to absorption or absorbance data. Okay, so if you recall your FTIR, you've encountered reflectance techniques, no? Yung ATR or yung DRS, diffuse reflectance spectroscopy. So even though they are reflectance techniques, the spectra produced is still interpreted in terms of absorbance or more commonly percent transmittance, okay, by the so-called Kubelka-Munk equation. So the Kubelka-Munk equation, I will not show it here anymore. It converts reflectance, alright, into absorbance data. Okay? Why absorbance? Because, well, as you will later see, absorbance is the one that has a relationship or direct relationship with concentration, no? Your Beer-Lambert's law. Alright? So basically, for any absorbance techniques, no, or techniques based on absorbance, Beer-Lambert's law is useful, no, for relating concentration, all right, with the instrument response. All right. Now we know that when matter absorbs electromagnetic radiation, there is excitation of electrons. All right. So when you say excitation, it is when electrons get promoted from a lower energy state to a higher energy state. Now, the picture of energy states between an atom and a molecule is quite different. All right? So for atoms, no, if your sample or your analyte is in atomic form, such as in AES or ICP, you have to realize that the energy levels that we're talking about are yung mga nasa Gen Chem notes ninyo, no? So 1s, 2s, 2p. So this is where electrons get promoted, no? Across atomic energy levels. But when we talk about molecules, such as in the case of FTIR or UVVs, wherein we are analyzing molecules, okay? We are not talking about atomic energy levels, 1s, 2s, 2p. But we are now talking about molecular energy levels. And take note, that molecular energy levels are the combinations of atomic energy levels, no? If you remember your LICAO, linear combination of atomic orbitals, all right, it results to your different combined energy levels, no? In organic chemistry, you are familiar with your sigma star, pi star, no? So those are the molecular orbitals. All right, you call them your molecular orbitals. In phychem, in quantum chem, another way to represent the energy levels of molecules is by using this terminologies based on density of states. No? So you have your singlet 1, singlet 2, you have your triplet states. All right? But no matter, no, the requirement for the promotion of an electron from a lower energy level to a higher energy level is that you have to excite that electron with energy from electromagnetic radiation equal to the difference in the energy levels between the lower state and the higher state. All right, so that's the requirement, no? And that's when we say that the energy, okay, is quantized, no, for atoms or for molecules alike.